Greetings, everyone. All right, so let's go over the practice exam solutions. This is number 4. This is the optional exam. And so the first question, we're given this piecewise defined function, and this is the graph of it. And the region R is all of this stuff here below the two curves and above the x-axis from -2 to whatever value that is on that end, pi squared over 4, I guess. We want to find the area of region R. Now, the thing with this one is we have to do this with two different integrals, and that's true for I think all the different parts, or maybe most of the different parts, because if you look to the left of 0, we have this function here, this parabola bounding the rectangle. Okay, put a little delta x here. But if you look from 0 and for positive values, we have a different curve on top. So I can't use one integral for this because the definition changes around 0. So I got to make sure I write two separate integrals for this. So finding the area, it is a fairly straightforward question. The area of R, so the first one goes from -2 to 0 of this 1/2 x plus 2 squared with respect to x, and then plus the integral from 0 to pi squared over 4 of the 2 minus 2 sine square root of x dx. And then we just, I think this is a calculator active question. I need to go double check that. So, because you can't do that second integral by hand. Yeah, this is a calculator active question. So all you have to do is write this down, write this series of integrals down, then go to your calculator and go compute it, and then come back and give the answer. That's it, okay? It's nothing more complicated than that. I'm going to pause the video to go get the answer. You should get about 2.268 for that one. Part B, it says for region R is the base of a solid. For the solid, each cross section perpendicular to the x-axis is a square. Write but do not evaluate. That's nice. It's going to save us some time. Write but do not evaluate an expression involving one or more integrals that gives the volume of the solid. Again, the same comment applies. From -2 to 0, we have one bounding function. And so the side length of the square over here is going to be this length right here, and that's given by the parabola, the first piece of the definition. And so this is the 1/2 x plus 2 quantity squared, and then I'll have to square that to get the actual area of the square. And on this region over here, this side length is the length of the square, 2 minus 2 sine root x. So I'll have to square that, and then I'll have to add the two integrals together. So it looks very similar to what we have up here in part A, but in part B, the volume, it still has the same boundaries, still same limits of integration, and I just get that side length and square it like this, and then from 0 to pi squared over 4, we get 2 minus 2 sine. Don't know why it jumped on me like that. I must have touched something with my arm, I guess. So, and that's it. Do not evaluate. That's probably 4 points. I don't remember, but quite a few. Okay, let's go back to part C. Let's go to part C. A lot of people misread this. Okay, so if you took this exam, be careful with this part, because a lot of you didn't notice or didn't understand that the 1 and 2 are bounding y values, not x values. But it says the portion of the region R for y 1 less than or equal to y less than or equal to y between 1 and 2 inclusive is revolved around the x-axis to form a solid. Find the volume of the solid. So there's several steps we got to do here. A lot of you used 1 and 2 as the limits of integration, but you shouldn't have, because 1 and 2 aren't x values. And so let me actually use this orange. Okay, we're looking between 1 and 2. So we're looking between this interval right here, the region of R between 1 and 2. So that's all of this stuff in here. This is the region that's going to be revolved about, I think it said the x-axis. I'm going to double check. Yeah, the x-axis. So again, I'm going to have to find or use two different integrals because I'm going to have two different bounding functions for my rectangles. So it's going to be like this. And again, we're revolving around the x-axis here if that was to extend like this. But what I need to do is I need to figure out what's the x-coordinate right over here so I know where to start. I know this first region is going to go from that x-coordinate, whatever that is, to 0. And then the second one's going to go from 0 to whatever point is right here, okay? That one, I don't know, so I'm going to have to go use my calculator to go figure that out. So I'm going to have to set the parabola equal to 1 because the horizontal line is 1. So 1/2 x plus 2 squared. Sorry, I'm just double checking. I need to figure out where that equals 1. That's a skill that I gave you on your calculator. And then the 2 minus 2 sine root x, I need to figure out where that equals 1 as well. And just in close to the y-axis. I don't need to go, it's a sine function, so it could equal 1 many times. No algebra, just go type that into your calculator and go figure out those points of intersection. I'm going to have to do that at some point. I'm going to call this one A, and I'll call this one B, and then I'll go back and find those values later. And by the way, you can actually, when you find those values, write down A is approximately this and B is approximately this. And then when you go write your integrals, you can just use A and B, and they'll say, oh, well, they know they're those values, and you'll have it right. You don't have to copy those numbers or retype or rewrite those numbers in multiple times. Now, since we're revolving around the x-axis and there's a gap between the edge of the rectangle and the axis of revolution, there's an empty space, this is the washer method. This is what we should be using here, the washer method. And if you remember the washer method for finding the volume, the integral from a to b, we had pi. Pi could either be out over here or it could be inside here, it doesn't matter, but I need the outer radius squared minus the inner radius squared integrated with respect to x, okay? So what's my outer radius? And again, I need to do this for two different integrals. So let's not forget that. So I'm going to need to go from a to 0, and then I'm going to need to add to that the integral from 0 to b, whatever that value is, okay? Both of them are going to have a factor of pi because we are revolving. We have a circle here, okay? Now, for the first function, or the first region, for less than 0, the outer radius is, I'm trying to make sure this is visible. I'm going to erase all this mess here. The outer radius is the edge that's further from the axis of revolution. That one's further than this one. These are the two parallel sides to the axis. The axis is the x-axis. And the one that's further away, that's this one. That length is the outer radius, and so that's that parabola. So we're going to have half times x plus 2 quantity squared, that's my outer radius. My inner radius, go back up here, it's the closer edge. Well, that closer edge is always on 1, and so my closer edge is 1, so minus 1 squared, and all that with respect to x. Same thing is happening for the other one as well. The outer radius is bounded by the function on that region, which is this 2 minus 2 sine root x. The inner radius is just 1 the entire time. And so this is going to be 2 minus 2 sine root x, quantity squared, minus 1 squared. And then we integrate all of that with respect to x. We're going to go plug that into a calculator, and I still need to go find a and b. I'm going to pause the video, come back with all those values for you. All right, so I went and like I said, I found the values of a and b by just using the calculator. I use Desmos, but you can do, you should be using your calculator. And then, actually, I didn't use Desmos because Desmos doesn't give me that many decimals here for this one, but I have another software package for the intersection because I want more decimal places. And then ran the integrals. You can either round or truncate. Remember 3 decimal places, please, for accuracy. All right, let's go into number 2. Oh, hold on, I gotta get a picture of this. All right, so we have a differential equation. We have a slope field. They're not going to have you draw this year on the AP, but you should at least understand how to do this. So in case they ask you questions about it, you can demonstrate your understanding. But that's the first thing. We have to draw this. So let's go back over to this screen here. And so dy over dx is 2 minus y over x. And we're looking at these 9 points over here. Now, if y equals 2, that's all these 3 points right here. 2 minus 2 is 0, and x is not 0 in any of those values. X is 1, 2, or 3. So these all become 0, and so we all get horizontal segments through here. And in the way they do the points, 1 point for all horizontal slopes and 1 point for all the others. So that's how they divided this one up for this one. Now, if we're looking at these points here, this is at 1, 3, okay? So if I plug in 3, I'm going to get a negative 1 in the numerator, and I get 1 for the denominator, so this is going to be negative 1. So I just try and line it up with negative 1, which would be down 1 over 1, so it should line up somewhere like that. If I plug in 2, 3, 2, so I still get negative 1. All the numerators here are negative 1, because we're always having y equals 3 for these 3 points. So negative 1 now over 2, so it's not quite as steep because it's negative 1 over 2, which would be something like this. It's a little less steep. Now it's negative 1 over 3, so it's a little less steep. Somehow show that if the slope's getting less steep, somehow make that clear in your picture. I'm not doing the best job of that, but that's what they want to see. They want to see the trend making sense. Now, for these 3 points, the numerator is always 1, because 2 minus 1 is going to give you 1, and then it's going to be 1 over 1, so we get a positive 1 here, so I'm going to line up at that point, and then it's going to be 1 over 2, so, imagine going up 1 over 2, so it'll be less steep, and then 1 over 3, less steep, like that, in a similar fashion. Just try to make it look reasonable. Oh, boy. All right, I had to log back in. So anyways, let y equal f of x be the particular solution to the given differential equation with the initial condition that f of 3 is equal to 1. Write an equation of the tangent line at y equals f of x and at x equals 3, use the equation to approximate f of 3.5. So y equals fx is a solution to this differential equation that they gave us up here. So that differential equation gives us the slope of the tangent line. And so when I go to work on B here, I know the slope of the tangent line is given by 2 minus y over x, and we're told that we're looking at the point where f of 3 is equal to 1. I'm going to double check that. Yeah, f of 3 is equal to 1. And so now if I evaluate this at the point 3 comma 1, means 3 for x, 1 for y. So that means I'm going to end up with 1/3 as my slope. And so the equation of the tangent line is going to be 1/3, y equals 1/3 times the quantity x minus 3 plus 1. And so f of, was it 3.5? You guys probably have this better remembered than me, is approximately 1/3, 3.5 minus 3 plus 1. You really could stop there, but let's see, that's half, that's a sixth, and once that's 7/6. That's pretty straightforward there. Part C, find the particular solution. This is where I have to solve the diff-EQ, okay? And there are a lot of little mistakes here, so let's work through this. dy over dx is equal to 2 minus y over x. And now I got to separate the variables. So I need to get all the x's on one side, all the y's on the other. Have to use algebra, no just random writing. I'm going to divide by 2 minus y and multiply by dx. So I'm going to get dy over 2 minus y equal to dx over x. Then I'm going to integrate. If you get it this far, you get a point. Better than nothing. I mean, I want you to get more than that, but let's accumulate points, ladies and gentlemen. This side over here, natural log absolute value of x plus c, straightforward. Okay, this side over here, you should do maybe a little substitution. Let's let u equal 2 minus y, so du. Actually, I'm going to do the side work over here because it's going to get crowded. Okay, a little bit of side work. So let's let u equal 2 minus y, so du is going to be negative dy. I don't have a negative, so I'm going to multiply by that negative here. So I need a negative du to balance things out. So this is the opposite of the integral of 1 over u du, which is negative natural log absolute value of u plus a constant, or negative natural log 2 minus y plus c. But I'm not going to use this plus c over here because I already got my plus c accounted for right there. I'm just going to make sure I have this negative natural log absolute value of 2 minus y over here. Okay. Now that we have that, let's go find c. We know f of 3 is 1. Again, I forgot. We're going to use that to find c. So we've got negative natural log, plug 1 in for y, 2 minus 1 is equal to natural log absolute value of 3, but that's still just 3, and plus c. 2 minus 1, of course, is 1. The natural log of 1 is 0. So all of this is nothing. Okay, so that means c is going to be the negative of the natural log of 3. If you can get this far correctly, this is 4 of the 5 points. Okay, this is almost all the points right here. There's a little bit of a challenge. Some of us struggle with finding, got this far and had trouble finding why, because you made some algebraic mistakes, but if you get this far, you got 4 of the 5 points, you're doing really well. First thing we want to do is get rid of this negative right here, because we're going to undo the natural log on this side, and I got to get rid of the negative to do that. So I'm multiplying through by the negative. Now I'm going to exponentiate, but I got to be careful. Okay, when I raise this side to the power of e and I raise this side to the power of e, the whole side is in the exponent here. I don't do a separate e over here. That's bad mathematics. Don't do that, okay? The whole side gets set up like that. This side over here can be separated into this by our log exponent properties. You know, if I have x to the power of a plus b, that's x to the power of a times x to the power of b, okay? So I'm just pulling it apart, okay? I'm taking, we're used to going this way, but it goes both directions here. So I just pulled the sum apart by putting a product in the base, okay? Why would I want to do that? Well, it's nice to do that because the e and the natural log here are going to cancel, leaving me with 3e to the negative natural log, the absolute value of x. Now, you might be thinking, can I cancel the e and the natural log? I can, but I have to get rid of that negative first. And right now I'm wondering if that's even worth it. So I'm not going to at the moment, but I can show you that later. All right, so over here, the e and the natural log cancel, leaving this absolute value, 2 minus y. And we got 3e to the negative natural log, absolute value of x. Now I'm going to drop the absolute value signs here. Whoops, I said drop them. And then I need plus or minus, like this. And then I got to continue solving for y. So negative y is going to be equal to negative 2 plus or minus 3e to the negative natural log absolute value of x. It's a horrible y, but anyways, now I'm going to reverse the signs to get rid of this negative. It means it's going to be a positive 2 and a negative and a positive. It seems weird, but we do that in mathematics. It's not that odd of a thing to do. I still need to choose one of these. Either I'm going to subtract or I'm going to add, but the question is which one is correct, okay? And we were told that f of 3 has to be equal to 1. And so I got to make sure I get 1 when I plug in 3, okay? I'm sorry, I'm just looking at the work at the moment here. I'm not sure which one is the correct one at the moment. What I thought was happening doesn't seem to be happening. So I'm going to separate these out here really quickly, just so we can see them. And then if I plug 3 into here, oh, I'm starting to see it now. Okay, this is, or maybe getting rid of that negative might have been helpful a little bit earlier. Let's see, e to the negative natural log. If I plug in, 3, I'm trying to see if this works. Now, to manipulate this here, I'm going to use another log exponent property. I'm not going to show you here. The log base b, I'm going to show you, of x to the power of a is equal to a log base b of x. So remember, I can bring the exponent down as a multiplier, but I can also put a multiplier back into the exponent, which is what I'm going to do here. I'm going to rewrite this to have this be 3 to the negative 1. So I can cancel out the natural log and the e, and I'm left with 3 to the negative 1. But 3 to the negative 1 is 1/3. And so I get 2 minus 1, which is 1, which is what I want. So this is going to be the correct answer right here. If we do something similar on this side and move, let's see, e to the natural log of 1/3. I'm skipping steps over here just so you can see it. When those cancel, you're going to be multiplying by 1/3, so you're going to end up with 3 as the answer, which is not the one we want, because when I plug in 3 for x, I should get 1 for y, not 3. That's why we want this one up here, because this one is the one that gave us the correct answer. Even if that last step was a little bit challenging, doing all of the other steps would have gotten you 4 out of 5 points, which is a lot. And if you would have got 4 out of 5 points, that would be an excellent job. I'm going to do a separate video for numbers 3 and 4 just due to time. I don't think I can get them in before the end of lunch. So I'm going to stop here and make another video later.